Today we'll be going over combination circuits. The notes are a little tricky today, but they're fairly short. So combination circuits involve a combination of series and parallel. So we need to review the rules for each, and so hopefully you remember these rules from last time. For series, the sum of the voltages is equal to the voltage equal to the voltage source. All resistors get the same current, and then if we want to find the equivalent resistance, we just add up all the resistances of the circuit. And then for parallel, each resistor gets the same voltage. The sum of the currents is the same as the total current from each source. And then the resistance is 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2 and so on. So when we go to combination, what we're going to do is we're going to use our VIR chart and we're going to rules. We're still going to use our VIR chart to organize our work. And we're going to use our rules to simplify the circuit into more manageable pieces. There's not really much else to say besides let's do some examples and see how this works. So let's look at this. We have a circuit with 4 resistors. And you can see here that we have a problem because it's not everything is in series. These two run in series with each other, but then it splits right here. And then so we have a parallel circuit within a series circuit. And so we got to figure out how to deal with that issue. So what we're going to do is we're going to do our VIR chart, VIR, do our columns for R1, R2, R3, R4, and the total, just like last time. Okay, and I'll leave a little work on the side to do some extra work. So let's look at R1. Let's write them all in. R1 is 5, R2 is 8, R3 is 8, and R4 is 6. Okay, and then this is 16. So unfortunately, we can't do the same thing we did last time with the R's and just add them all up because it's not all in series, and we can't do the inverse rule because it's not all in parallel. But what we can do is realize that these two are in parallel with each other. So instead of what we can do is we can kind of, on this last side, it kind of shows it. If we have two in parallel with each other, we can use our parallel rule to simplify it into a different circuit. So let's use our parallel rule here and simplify the circuit into a different resistor. So let's find the equivalent resistance of this section right here. The equivalent resistance of that section, let me do it down here, 1 over R is equal to 1 over R1 plus 1 over R2. But in this case, it's 1 over R2 plus 1 over R3 because those are the variables we're talking about. So it's 1 over 8 plus 1 over 8, which ends up giving us 0.25 if you put in your calculator. Which means that, remember that the second step is we need to do 1 divided by this number. So we get 4. So that means that this parallel branch acts as if it has a resistance of 4. And so now we can find the total of the resistance of the circuit by doing series, because now we have a resistance here, which is 5, a resistance here, which is 6, and then an equivalent resistance for that section of 4. And so we can just add all of those. We get 4 plus 6 plus 5, which gives us 15. And then now we can run the work backwards. And so if we use V equals IR, we can get that the current here is 4. And we know in series, the current is the same throughout. And so each of the resistors in that series section are going to get 4. But we know that the current's going to split off in that last section. Okay. So we can't necessarily do anything just yet, so we'll wait. But what we can do is we can fill in these V's. Again, 2 rows by V equals IR. So we get 20 here, and we get 24 here. So that means that the voltage of the section coming into the section is 60 minus 20 minus 24 using our rules. And we get 40 minus 24, which is 16. And remember that parallel is the same voltage throughout. And so that means each branch gets 16. And then again, we can use V equals IR to get these last two things. It's a lot. It's kind of, hopefully it makes sense. But at the same time, it takes some practice, it takes some review. I would recommend going to other tutorials too, and then just look through a lot of examples. Look through a ton of examples of how it's split up. Look through other ways they reword this. Let's do another one. This time we have VIR. And then we have R1, R2, R3, R4, and total. This will be the last one we do. R1 is 50, R2 is 100, R3 is 75, and R4 is 125. And then our total voltage is 120 volts. Okay. So here we have two series circuits that are in parallel to each other. So it's a little bit different of a problem. So instead what we can do is I can find the equivalent resistance for this series branch, and then I can find the equivalent resistance for this series branch, and then I can put them into a parallel equation and find the equivalent resistance for the whole thing. So essentially what I'm saying is that let's first find this first thing. Since these are in series, if we want to find the resistance, we just add them up. So we get 150 here, and similarly we get 200 here. And so what I'm claiming is that because they're in series, they act as one resistor of 150 ohms. And this acts as one resistor of 200. And so in a sense, what we're doing is we're getting another parallel circuit that looks more like this. Okay, where 1 is 150 and 200. Because they're in series, that we can use those rules to simplify the circuit down. And then now we have a parallel circuit. And so we can just find the equivalent resistance of the series of a whole by doing 1 over R equals 1 over 50 plus 1 over 200. Which, let me put that into my calculator. And I get 85.7. And so that is our equivalent resistance for the series. I can do 120 divided by that. I get 1.4. Okay. And so now I'm going to delete a lot of these markings I made. So now remember our rule for voltage. Voltage is the same for each parallel branch. And so both of these branches get 120 volts into it. They're splitting up the current, but each one gets 120 volts. Okay. And then remember that this branch's equivalence is 150 and this one is 200. And so we can use that to find the current. The current through this top branch is 120 divided by 150. 120 divided by 150 is 0.8. So that means the current for that top branch is 0.8, and we know the current is the same throughout the series. And so the top two both get a current of 0.8. In the bottom branch is 120 divided by 200, so we get 0.6. And we can double check that because, again, the top branch gets 0.8 current, the bottom branch gets 0.4 current, which add up to 0.6, my bad. We just found 0.6. That adds up to 1.4, which was our total current entering the system. So 0.8 goes up, 0.6 goes down, goes throughout, and then we can use that to find V. We know our I and R for each thing, and so we're going to use that to find V. 0.8 times 50 equals 40. So that means this is 42, and then 0.6 times 75, 45. And then, wait, no, my bad. 40 times, or 0.8 times 100 is 80. That should be 80, my bad. And that's 45, and then 0.6 times 125 is 75. And that should make sense because each branch gets 120 volts. And so these top two should both have a total voltage of 120. And these bottom two should both have a total voltage of 120 because each branch gets 120 volts. So what makes this hard is we're combining these rules, and it takes some thinking. There's not an exact process to go through. The main process is simplify it down. Work with equivalent resistances using our rules and try to simplify the circuit down into just one series circuit or one parallel. So what we did here is we simplified this top branch and this bottom branch into a series of one resistors by using our rules of equivalence. With that, you should be able to get some practice on the assignment, as well as do the gizmos. If you're still lost, try doing the gizmos. They work their advanced circuits as well, and they also explain how to do and how to tackle and how the equivalency works. And so try the gizmos out if it's still confusing. I think this gizmos especially is one that is more suggestive than others because it really helps get you more understanding of how to do this. With that, I am done. Have a good day.